Let's look at discussion 10. So right now we want to sketch the potential energy of a simple harmonic oscillator under the condition that this particle has a negative total energy. So let's write our total energy somewhere here, which is a negative value. Here's our total energy. So we can achieve this by shifting the arbitrary constant u0 in our potential energy. The definition of that is that when we have our potential energy, we can have 1 half k x minus the distance from the uh, equilibrium position, which is x0 squared, and then we can have a constant here. So if we have this constant to be so negative, then we can shift the total energy all the way down to negative. And we know that the total energy is kinetic energy plus potential energy, and kinetic energy is always bigger than 0. So it means that to have a negative total energy, we must have a negative potential energy, and we want to have a negative u0, and it should be below the total energy. So we have that because this is bigger than 0, u is smaller or equal to E total, and therefore, and because in potential energy, this term is also bigger or greater than 0, bigger or equal to 0, so we know that this u0 must be smaller than the total energy, so we need to draw our potential energy constant here, and that's where we draw our u0. So now we can set the position of equilibrium at a positive value. Let's set it here. Here's our x0, and let's draw some and we draw it very far away from the 0 point, and now we can draw the potential energy diagram. So at x0, the potential energy is the constant u0, so it starts right here, and as it goes up, it grows like a curve, and more exactly, it grows like a parabola, so it has the shape of this. The reason that we stop here is because when it stops there, so the particle will stop, it will oscillate around here until the kinetic energy is 0. So when kinetic energy is 0, the total energy is just the potential energy. So once the potential energy reaches the total energy, then the particle will stop oscillating. So we know that this is the range of the oscillation of the particle, and then this will be the turnaround points, which is the intersection here and here. So these are the so-called turnaround points. And for number 2, we have this formula for our potential energy, and we know that u0 should be smaller than 0. So for part 3, we want to figure out the amplitude. So as we said, these 2 points are turnaround points, and therefore the particle will only oscillate inside this range. And the definition of amplitude is not this entire range, but the distance of the range to the equilibrium position. So here is the amplitude, and we want to figure out the amplitude in terms of the quantity above. So we see that at here, this is x0 plus a. So the potential energy at x equals x0 plus a should equal to the total energy here. But because now our potential energy has a extra constant u0, so after we plug in x equals x0 minus plus a, we see that it is not just what we have as usual. It becomes 1 half k a squared plus u0 becomes E total. So the thing is wrong. And we want to extract the effective K from our new equation. So because the oscillation is only related to the distance away from the equilibrium point, we can define small d to be the x position away from equilibrium point. Then we found that our potential energy is just 1/2 k d squared with a constant, and this constant is just a constant. We can make it 0 again. So we see that for this shift of x naught, it's not going to change the frequency of oscillation, and omega 3 is still k divided by the mass of the particle. And now we want to have a mathematical method to get k from our potential energy function. So we see that the k is something related to the distance from equilibrium position squared. There's an easy way to do it. We just need to differentiate it. Then we can get rid of this u naught because it's a constant. And if we differentiate it again, we get rid of x naught because that's also a constant, and we just get k. So we can just differentiate the potential energy twice to get the constant k. And the second derivative of a graph is the curvature. So we get that the curvature at x naught will give us the value of k. And it can work for any function that looks like a simple harmonic oscillator.